16 million seismograms, 24 data processing centers, three-quarters of the lower mantle layer scanned for the first time in the history of observations. When Jonathan Wolf's team from the University of California, Berkeley, published a global map of deformations at the core mantle boundary in April 2026, the scientific community received an image that had never existed before. A map showing how deep beneath the planet's surface, ancient tectonic plates, which plunged into the mantle millions of years ago, continue to twist, squeeze, and deform rock at a depth of 2,900 kilometers. Directly above the boundary where the glowing liquid iron of the outer core meets the lower mantle. Leave a comment letting us know where you are watching us from. And we continue. This map in itself would have been the event of the year, but it came out at a time when the Earth's core was already sending signals that scientists had been recording over the past 2 years, and each new signal added more questions than answers. In February 2025, John Vidal's group from the University of Southern California confirmed what seismologists had been arguing about for more than a decade. The planet's inner core, a solid sphere of iron and nickel about 70% the size of the moon, rotating at a depth of 5,100 kilometers, has slowed down. Not just slowed down. The data showed that from around 2010, the core began to lose its rotational speed relative to the surface and then reversed. It is rotating in the opposite direction. Vidal's team analyzed about 200 pairs of repeating earthquakes from 1991 to 2024, recorded by stations in Alaska and Canada. Waveforms that should have matched did not. 10 doublets showed differences that can only be explained by one thing: the core changed its pattern of motion. That was in February. In December 2025, the next signal arrived. Researchers from Sichuan University and the Institute of Geochemistry published experimental evidence that the inner core does not exist in a normal solid state, but in a so-called superionic phase, a state in which carbon atoms move freely through the iron crystal lattice, like a liquid inside a solid body. The core turned out to be softer than all existing models suggested, and between these two discoveries, in the middle of 2025, the European Space Agency published 11 years of magnetic field monitoring data. The South Atlantic anomaly, an area of abnormally weak magnetic field over the South Atlantic, grew by an area comparable to half of continental Europe, and its expansion rate increased after 2020. 3 signals from the deep. 3 different parameters, 1 system. And now, in April 2026, Wolf's global map showed that a large-scale deformation is occurring at the very boundary where the outer core touches the mantle. Not local, not point-like, covering 2/3 of the surveyed area. This is not a single event. This is a sequence. And to understand what it means, you need to go down. 4 discoveries in 14 months, and each of them concerns the same zone, the deep layers of the planet where no instrument penetrates directly. But before connecting the dots on the map, it is worth understanding how the space itself, from which these signals come, is structured. Because most people imagine the inside of the Earth as a simple diagram from a school textbook: crust, mantle, core. 3 layers, 3 colors. The reality is different. The Earth is not a layer cake. It is a machine with moving parts, each of which affects the others. Let us start from the center. At a depth of approximately 5,150 kilometers lies the inner core, a sphere with a diameter of about 2,440 kilometers. Until recently, it was believed to be a monolithic piece of crystalline iron compressed by a pressure of 3.3 million atmospheres and heated to a temperature comparable to the surface of the sun, about 5,400 degrees Celsius. The model was simple: a solid body surrounded by liquid, held by gravity. Textbooks described it as something stable, almost inert. This model no longer works. Vidal's data showed that the core does not just rotate, it changes its rotation pattern with a periodicity that different groups estimate differently. Some speak of a 6-year cycle. Others talk about a 70-year cycle. Still others record a single jerk in the early 2000s and relative stability afterwards. There is no consensus. But everyone agrees on one thing. Since about 2010, something has changed. The rotation speed of the inner core relative to the surface dropped, and then the core began to move in the opposite direction. Not fast, not catastrophically, but measurably. Now add to this the superionic discovery. Professor Yujun Zhang's team bombarded samples of an iron-carbon alloy with shock waves, accelerating them to a speed of almost 25,000 kilometers per hour. At pressures and temperatures approaching the conditions of the inner core, the samples became sharply softer. Carbon atoms began to migrate freely through the iron crystal lattice without destroying it. The iron remained solid. The carbon behaved like a liquid inside this solid body. The superionic phase, a state that is neither a classic solid nor a liquid, but something third. This explains a riddle that has plagued seismologists for decades. Shear seismic waves passing through the inner core slowed down more than models for pure solid iron predicted. The core behaves softer than it should have. Now we know why. But this knowledge poses a new question. If the core is softer than believed, if atoms move freely inside it, if its rotation is unstable, how stable is the system that generates the planet's magnetic field? Because the magnetic field is not born in the inner core, it is born one floor above. In the liquid outer core, a layer of molten iron about 2,200 kilometers thick that surrounds the solid sphere. It is there that convective flows of metal, driven by the heat and rotation of the planet, work like a giant dynamo. And it is from there that the next signal comes. The liquid iron of the outer core moves at a speed of about 40 kilometers per year, slower than a human fingernail grows. But these flows are enough to maintain the electric currents that generate the magnetic field extending tens of thousands of kilometers into space, a field without which the solar wind would have stripped away the atmosphere long ago. And it is this field that is now behaving like it has not throughout the entire period of satellite observations. The South Atlantic anomaly was first described back in the 19th century, a zone over the southern part of the Atlantic Ocean, southeast of South America, where the magnetic field strength is noticeably lower than in surrounding regions. For a long time, this was considered a regional feature, interesting but not alarming. Satellites flying through this zone received an increased dose of radiation, and electronic glitches occasionally occurred. Operators learned to work with this. Scheduled reboots, protective protocols, and inconvenience, nothing more. But in 2025, the European Space Agency published the results of 11 years of monitoring conducted by 3 satellites of the SWARM mission. These devices were designed specifically to measure magnetic signals from the core, mantle, crust, and ionosphere. 11 years of continuous measurements. And the picture they showed turned out to be more complex than expected. From 2014 to 2025, the South Atlantic anomaly expanded over an area comparable to half of continental Europe, about 2 million square miles. By 2025, its eastern edge had crept almost to the coast of South Africa. But it is not just about size. The anomaly has changed its structure. If previously it was a single zone of weakened field with one minimum, then by the 20s, 2 separate minima formed inside it, 2 centers of weakness. The western one, located at approximately 60 degrees west longitude, and the eastern one, near the prime meridian. And these 2 centers behave differently. Chris Finley, professor of geomagnetism at the Technical University of Denmark and lead author of the study, described it this way. The anomaly is not a single block. It changes differently near Africa and near South America. The eastern minimum lost about 600 nanoteslas of field strength between 2018 and 2025. The western one lost about 200, a 3-fold difference. This is not a uniform weakening. This is asymmetry. And here's a detail that Finley drew attention to. In the anomaly zone, the magnetic field lines, which normally emerge from the core upward, reverse in some places and go back down. The field seems to be drawn back in. The reason for this behavior does not yet have an unambiguous explanation. But the fact itself indicates that processes at the boundary of the outer core and mantle, in the very layer mapped by Wolf's team, directly shape what happens to the magnetic shield. One phenomenon is below, another is above, and between them are 2,900 kilometers of rock through which the signal passes. a signal we are just beginning to read. A signal from below and a signal from above. Deformation at the core mantle boundary recorded seismically, and the weakening of the magnetic field recorded from space. Two datasets obtained by different instruments, at different institutes, for different purposes, but pointing to the same zone. And if you overlay them on each other, something appears that none of the teams stated directly, but which is hard not to notice. Wolf's map showed that seismic anisotropy, a sign of deformation, was found in about 2/3 of the surveyed area of the lower mantle. But the distribution is not random. Most of the deformation is concentrated in zones where geodynamicists estimate deeply plunged tectonic plates are located. Plates that began their plunge at the surface millions of years ago passed through the entire thickness of the mantle and reached the boundary with the core. There, at a depth of 2,900 kilometers, they do not disappear. They deform. And they deform the material around them. Wolf's team used 70,000 differential measurements of shear wave splitting. Waves of the SKS and SKKS type, which pass through the core and mantle along different paths, allow the detection of zones where the propagation speed depends on direction. It is like a beam of light passing through a crystal. If the structure of the material is oriented in a certain way, the beam splits. Seismic waves split the same way in deformed rock, and these splittings turned out to be everywhere. Now the question. These ancient plates lying on the core boundary press on it from above. The liquid iron of the outer core presses from below. Convective flows that generate the magnetic field pass exactly through this boundary, reacting to its topography. If the boundary is deformed, the flows change direction. If the flows change direction, the configuration of the magnetic field changes. If the field configuration changes, zones of weakening appear on the surface. Correlation does not mean causation, but it means that the question is worth asking. And the question is this. Could the large-scale deformation at the core mantle boundary mapped in 2026 affect the behavior of the convective dynamo in the outer core, which in turn creates the observed changes in the magnetic field, including the growth of the South Atlantic anomaly? No peer-reviewed article yet claims this directly, but the components are lining up into a chain that is hard to ignore. There is also another element. The core mantle boundary is heterogeneous. On it exist two giant structures known as large low shear velocity provinces, LLSVPS. One is located under Africa, the other is under the Pacific Ocean. Each of them has dimensions comparable to a continent. Their nature still remains a subject of discussion. Some models describe them as zones of abnormally hot material, others as masses chemically distinct from the surrounding mantle, possibly existing since the formation of the planet. The African province is located directly beneath the region where the South Atlantic anomaly demonstrates the most rapid weakening of the field. A giant structure under Africa, trillions of tons of anomalous material at the core boundary, and right above it, a zone where the planet's magnetic shield is weakening fastest. This coincidence has been noted in the literature before, but until 2026, there was no global deformation map that would show what happens around these structures on the scale of the entire boundary. Now, such a map exists, and it adds another dimension. Wolf's data showed that anisotropy is concentrated not only in the zones of plunged plates, but also along the edges of those very large provinces, LLSVPS. At their boundaries, the mantle material experiences the greatest stresses. Where a slow flow meets the wall of an anomalous province, the rock twists, becomes oriented, acquires texture. It is at these boundaries, according to geodynamic models, that upwellings arise, mantle plumes that rise to the surface and feed volcanic chains. But if the boundary of the province deforms the mantle from above, what does it do to the liquid iron from below? Convection in the outer core does not occur in a smooth spherical shell. It occurs in a space whose upper boundary has relief, mountains and valleys. Studies have recorded height differences at the core mantle boundary of up to 14 kilometers. This is not a smooth surface. It is a landscape, and convective flows of liquid iron flow around it like a river flows around boulders. Now let us add to the picture what is happening at the other end of the system, in the very center. In December 2024, 2 months before the publication of the data on the rotation reversal, Vidal's team discovered something it did not expect. Analyzing 121 pairs of repeating earthquakes near the South Sandwich Islands from 1991 to 2024, researchers found doublets whose waveforms were not explained by rotation. The differences indicated that the inner core is not just rotating and slowing down, it is changing shape. Vidal described the moment of discovery like this. He was studying graphs of seismic oscillations when one dataset stood out among the rest. Later, he realized that he was looking at evidence that the inner core is not absolutely solid in the classic sense. The superionic discovery of 2025 confirmed this experimentally, but seismic data recorded the consequence before the laboratory experiment explained the cause. A core that slows down, a core that is softer than believed, a core that changes shape, a boundary that is deformed over 2/3 of its area, a magnetic field that weakens unevenly and becomes structurally more complex. Each of these facts is documented by a separate study published in a peer-reviewed journal based on independent data. None of these studies claims a connection to all the others. This is not their task. Each team works with its own fragment, but when you put the fragments side by side, the outline begins to emerge. And this outline indicates that the deep dynamics of the planet have entered a phase whose parameters go beyond what was observed in the era of instrumental measurements. At the time of recording this episode, no agency has issued a formal warning. Monitoring continues. The outline that emerges from the deep data concerns processes unfolding on scales of thousands of kilometers and millions of years. But the planet does not wait for scientists to assemble the full picture. Events continue to accumulate on the surface and in near space, each of which deserves separate attention. In April 2026, simultaneously with the publication of Wolf's map, another study came out that attracted less attention but is no less significant. A team from international laboratories published experimental data on the mechanism of deep earthquakes, those that occur at depths from 410 to 600 kilometers in the mantle transition zone. It was believed that at such depths, frictional sliding of faults is impossible due to colossal pressure. Nevertheless, seismicity in the transition zone not only exists, but increases with depth. The study showed that the reason is phase transitions of the mineral olivine under the conditions of cold subducting plates. Olivine, the main mineral of the upper mantle, undergoes a structural rearrangement at certain pressures and temperatures, and it is at the moment of this transition that the rock becomes brittle. The crack arises not despite the pressure, but due to a chemical transformation. This is important in the context of the main topic. Those same plunging plates that Wolf recorded at the core boundary pass through the transition zone, generating deep earthquakes along the way. The mechanism is now experimentally confirmed. The plates do not just sink. They transform, break, and deform the environment at every stage of subduction, from 400 to 2,900 kilometers. Separately, it is worth noting that in January 2026, NOAA and the University of Colorado released an updated high-resolution geomagnetic field model, HDGM 2026. The update was driven by practical necessity. The model is used for navigation during well drilling, and the previous version had begun to give noticeable errors. The new model for the first time included a real-time correction for disturbances from auroral electrojets, powerful electric currents in the ionosphere caused by the interaction of the solar wind with the magnetosphere. These currents are particularly strong in polar regions and are capable of distorting magnetic measurements so much that drilling operations lose accuracy. The very fact that the model required an urgent update speaks to the speed of changes. Geomagnetic models are usually revised once every 5 years. Interim corrections indicate that the field is changing faster than previous versions predicted. And one more element to record. Swarm data showed that, simultaneously with the weakening of the field over the South Atlantic, changes are occurring in the Northern Hemisphere. Magnetic intensity is rising over some regions and falling over others. The two poles of magnetic activity in the Northern Hemisphere behave asymmetrically. This is not a local phenomenon. This is a redistribution. The field is not just weakening in one place, it is restructuring globally. Restructuring is underway on all floors, from the inner core to the ionosphere. And the pace of this restructuring, judging by the fact that the navigation model update could not wait for the scheduled cycle, is accelerating. The pace is accelerating. Models become obsolete faster than they are updated. And if we step back from the details and look at everything said as a single map, what emerges is not a catastrophe, not a prediction, but something perhaps more important: the scale of ignorance. Here is what we know as of June 2026. The inner core has changed its rotation mode. It has been experimentally confirmed that it exists in a superionic state in which light elements migrate through the crystal lattice. There is seismic evidence that the shape of the core is unstable. A global map of the lower mantle showed that deformation at the core boundary covers 2/3 of the surveyed area and is associated with ancient subducted plates. The magnetic field has weakened over the South Atlantic by an area equal to half of Europe, with an acceleration after 2020. Inside the anomaly, two minima have formed with different rates of weakening. Magnetic field lines in the anomaly zone reverse and go back into the core. In the northern hemisphere, the field is redistributed asymmetrically. Here is what we do not know. We do not know whether the changes in the rotation of the inner core are connected with changes in the magnetic field causally or only correlationally. We do not know whether the superionic state of the core is a permanent property or if it can change depending on thermal conditions. We do not know exactly how the topography of the core mantle boundary affects the configuration of the convective flows that generate the field. We do not know whether the current weakening of the South Atlantic anomaly is part of a long-term cycle or the beginning of something without parallels in instrumental history. And here is what makes this combination unusual. For the first time in the history of geophysics, data on the behavior of the inner core, the state of the core mantle boundary, and the configuration of the magnetic field were updated almost simultaneously. Previously, each of these layers was studied for decades, and results were published at intervals that did not allow synchronicity to be seen. Now, thanks to the density of seismic networks, satellite monitoring, and computing power, the picture is coming together in real time. And it shows not a stable system with local deviations, but a system in which several fundamental parameters have shifted simultaneously. The interpretations heard here are analytics, not scientific consensus. The links between events are questions, not statements. For up-to-date safety information, there are always the USGS, NOAA, ESA, and local monitoring services. But the data we see do not yet add up to an unambiguous picture. And ambiguity at such depths and scales is not a reason for calm. It is a reason for attention. The planet does not send warnings in the human sense of the word. It has no intentions. But it has parameters that can be measured. And when several of them change simultaneously, in one direction, with increasing speed, it means at the very least that we are observing a process whose boundaries have not yet been defined. Where these boundaries are is a question that the next years of observations will answer. The following years will show where the boundary of the process lies. But waiting for an answer does not mean a pause in events. While we wait, the system continues to work. Every second, the liquid iron of the outer core makes its slow turn. Every second, convective flows redistribute heat from the inner core to the mantle. Every second, the magnetic field generated by this movement either strengthens or weakens at points that the swarm satellites will record on their next pass. The swarm mission continues its work. Data are coming in. The next generation of satellite measurements will determine whether the current phase of weakening is a temporary fluctuation or part of a larger trend. Professor Finley and his colleagues from the Technical University of Denmark explicitly pointed this out in their publication. There is no answer yet. John Vidal and his group continue to track the rotation of the inner core. Each new repeating earthquake recorded by stations in Alaska and Canada adds a point to the graph. If the rotation reversal is part of a cyclic process with a period of several decades, as some models suggest, then in the coming years the reverse rotation speed should stabilize. If this is not a cycle but a transition to a new mode, the graph will show otherwise. Wolf's map covered 75% of the lower mantle. The remaining 25% are zones where the density of seismic data is insufficient. The absence of a signal in these zones does not mean the absence of deformation. It means that we do not see it yet. Wolff himself pointed out this limitation. The map is incomplete. But even incomplete, it changed the understanding of how active the boundary between the two main layers of the planet is. 16 million seismograms. This is the number with which this episode began. Each seismogram is a record of a vibration caused by an earthquake somewhere on the surface, passing through the entire thickness of the Earth and returning to the top to a receiver. On the way, the wave passed through the crust, upper mantle, transition zone, lower mantle, outer core, perhaps touched the inner core, and returned back, carrying within itself information about each layer through which it passed. Information encoded in delays, splittings, attenuations. We have learned to read part of this code, enough to see that the core has slowed down, that it is softer than thought, that the boundary is deformed, that the field is weakening and restructuring. But this is only a part. What exact part of the whole it is, we do not know yet. 3,000 kilometers of molten iron, 5,000 kilometers to the center, the temperature of the surface of the sun, pressure of millions of atmospheres. And the only way to look in there is to wait for the Earth itself to shudder and listen to the echo. The echo continues to come, we continue to listen.